This conference will now be recorded.
Either 1x4 or 2x2. I got to turn on my speaker now. A 1x4 or 2x2. Speaker. Bear with me 1 second, folks. Spread spectrum control. There are a couple pins that are. Is there any way to mute that? Yeah, I did mute it on the computer, but it keeps turning back on. I'm going to talk over here, and we'll let Jason worry about that. Spread spectrum control. So PCIe NVMe has a couple pins for ref clock for both interfaces, and that was made for plug-in cards to have their own reference clock. Those signals don't make as much sense on a hard drive where you have to have your own frequency reference on the drive device itself. I did it, but it's...
Try that.
Oh, thank you.
Sorry.
Some audio difficulties in the room. Hopefully we're good now. So spread spectrum, you know, there are things that are needed for that. Out-of-band I/O, so SM bus. I don't know how familiar people are. Just a show of hands, how many people know what SM bus is? Okay, so a fair number of people in the room. Whether we support SM bus, for those of you who aren't, I'll talk about it in a few slides and what it entails. And with SM bus comes the option for doing unpowered vital product data. Basically, you back power in a little trickle of current on the SM bus, and you can read an EEPROM for that. Whether or not that feature has value in a hard drive storage array is something that I think a standards committee needs to look at. Resets require pins. They're extra system signals, whether we support those. The connector I'll talk about later, and then 12-volt only is another good example of something that a standards committee should talk about, because you know that obviously that has big impact for both the device and the system power supply. So connectors, 8482. This is the typical SAS connector. I think most of us know it. The 8639 is I kind of view it as a superset of the 8482. It adds many more pins. This was to support 4 independent lanes on an SSD apart from the 2 lanes for SAS, and I'll go through detail there. Now, why am I talking connectors here? One thing that we're really concerned about with hard drives is that this connector adds 2 sets of rows of pins here. On a solid state drive, they center mount this connector. It's right on the board. Not a big deal, although you know the cost of the connector is a consideration. But on a hard drive, we're offset and we're at the bottom of the drive, and that second set of pins is potentially nearer to the base casting. That's a mechanical challenge for us. There's also signal integrity concerns with that, so we're taking a serious look at the connector. U.2 versus U.3, for people who are not familiar with it. U.2 puts the PCIe lanes on the connector on different pins than what you would use for a SAS. So if you see on the right here, SAS shows lane 0, lane 1, or port 0, port 1 in SAS vernacular, versus PCIe, where they're on different pin locations. U.3 changes that, and so newer SSDs, ones that support U.3, support this sort of configuration where they use 0 and 1 in common with SAS. Why we like that is where we put the pins on our controller ASIC and how we port it out for the wiring on the card. We like to optimize it for one design or the other. This is not if we want to go this way and support both SAS and U3 using the same ports on the controller, it's not as optimal. So there's a preference to follow this standard here, but what we need to know is if you know people are building systems and are wanting to stuff both U.2 solid state drives in with these, then that may not be popular with people who are building systems like that. So this goes into a little more detail on some of the pins involved here. So if we can just narrow it down to U.3, the extra pins here I've highlighted in red. These are the ones that are most critical. There are a few others, HPT 0 and 1, which may be debatable as to whether you would include them, whether a hard drive would need them for ordinary functioning. But you can see if we can narrow down to a common set of a limited set of pins, we potentially can make a cheaper connector and still support the same functionality, which is beneficial to us all. U.2, this shows the number of pins we would have to add. to support U.2, so we have to add both those sets of pins there, as well as some of the discretes and shown in the other connector. SM bus. So basically, SM bus is a low bandwidth I2C interface that that goes between a system management controller and a storage device, and it has a long legacy. It goes back to PC systems that allowed PCs to have a simple interface to figure out what's plugged into each PCIe slot, and it's carried forward here. There are challenges with PCIe for us from a cost perspective and parts perspective. So let me go through a few of the challenges that they're running into on both SSDs right now. For one thing, these are specified to be 3.3 volt tolerant IOs, but actually in practice they have to be 5 volt tolerant IOs, which generally means you have to buffer them on the drive. There's a problem with the interface where one of the drawbacks with an I2C interface is if you drop a clock on I2C, the interface can hang. And so right now on SSD, there's talk about either adding a reset signal, or if you drop power, that the target device has to reset. It's more complexity. And then there's system complexity in having, if you have 100 drives in a 4x, having to fan out I2C connections from the host to all those drives. So, from an open compute standpoint, we really have to decide, is this something we want to carry? The advantages of it are you could tell what's in your system without applying full power to the device. But we could also do that over the interface like SAS does today. The challenges with it, though, are with the integration and the extra costs are real here. So that's something that has to be debated. The other thing with SM Bus is that the interface supports doing all of the commands that SM Bus supports over the native interface. So you really have to decide whether out of band is wanted or not. With all these things, it's something that we certainly can support and may support. It's just it's cost. So arriving at a standard agreement, whether people really want these or don't want these, to help make those trade-offs is the purpose for a working group. So the connector. So there's a large section of backup slides in here. Taking a look at it, we potentially could do, if you want to do a more stripped down version of NVMe, you could potentially support this with a SAS connector. And, without getting into internal proprietary stuff, we've started to quote this, and it's on the order of between 50 cents and $1 for the difference in cost between the connectors. So it's not a whole lot of cost, but it's still real. And when you multiply anything times 20 million drives, it starts to become real money. So you have to decide 12 volt only or not 12 volt only, 5 volt and 12 volt. If we free up the 5 volt pins, then we can support things like resets. But to support like an 8482 connector, we would have to drop some features such as the SM bus, the ref clocks, and we would require SRIS on the host bus adapter. So really, we're kind of focusing, we've kind of narrowed it down internally to a couple of configurations that we would recommend to a committee. And between the two of them right now, we're kind of favoring the U.3 configuration because it provides the most support. But if we can get away with not having to support everything, then there is a cost savings out there for the 8482 connector. That's really all I had to talk about today. So the message, I guess, here is I think, and I'll share a PDF of these slides. You're welcome to have them, so don't worry about copying them. I just wanted to kind of lay out some of the issues that that go along with NVMe and PCIe, and hopefully make a case that I think it merits a working group for Open Compute to work through these, maybe develop to a standard to try and get something that's optimized for both vendors and customers, ideally. So with that, I'll take any questions or comments.
So which working groups have you been discussing with, or is this just...
This is the first time we've talked about this at all. It's been internal to this point.
What is SRIS?
Okay, yeah. So SRIS is, what is it? Source Ref Clock Independent Spread Spectrum. Basically, how SAS works, where each device does its down spread independent of each other. Host bus adapters newer host bus adapters from some companies support SRIS. Probably some of I would imagine maybe the cheapest ones don't. I don't know. I haven't done a full survey of the market. But that, is something that, are we okay with the limitation of SRIS? That has other benefits to us. So I mentioned the ref clock signals. Those are 100 megahertz signals. They have to get fanned out from the source or from the switch to every device. It's highly desirable if we can get rid of having to route 100 megahertz signals throughout a chassis to get rid of those, because they're really not essential to this function if you have an SRIS compliant host bus adapter. Yeah. Right. Yeah. Yeah. So, I talked probably too briefly about the port or lane configuration control. These devices, you can either have all the lanes gang together, kind of like SAS wide port, where you get a very high bandwidth single interface, or you can split them into two independent ports for high availability. And how you configure a device, how they do it in SSDs, they actually have a strap on the back plane, and the device reads that strap and either comes up in like a 2x2 or a 4x1 configuration, or 1x4, I should say, configuration. Likewise for hard drives, we could follow that convention. We could have hardware straps. The main concern with hardware straps is just that if you get it wrong, you have a potential reliability issue in the system. The other way we could do it would be software-wise configuration. And that would either have to be negotiated over the interface, or you would have like a mode control bit, to use SAS parlance, where the device would be configured out of manufacturing to the customer's liking. So either if we're going to go with 2 lanes, it would either be a 1x2 or a 2x1 configuration. And so that's another thing. Whether people would prefer a hardware strap for doing that sort of determination, or a software strap, or you could even do both potentially. You could tell the mode use the hardware strap. That's an option. So that's kind of the purpose of a working group, is to try to nail down some of these attributes. Were there any other points or things you wanted me to talk through there? Yeah, so we would, if we went 12 volt only, yeah, another thing I should mention is a lot of these newer SSDs are 12 volt only, and we've mulled that in hard drives for years, going 12 volt only, and it's kind of unfortunate that we didn't go that way on SAS, at least in my mind, because a lot of the systems just put a little 12 to 5 volt regulator on the back plane next to each drive. But if we do go 12 volt only, that frees up 3 pins that we can use for other things, possibly resets or other functions. I should talk about resets too. I didn't get into that much. PCIe has discrete reset pins for resetting the host interface. On SAS, they're done. You don't have those. They're done in-band. PCIe interface also supports in-band resets. People, system builders, some of them have come to rely on those hardware pins, even though they can be done through the interface. And there's certain software and BIOS, behaviors that may come to rely on it. They're not essential, but we'd all have to agree that we do it over the interface. Otherwise, we got to put the pins in. Yeah. So the question was, what is the IOP gain? And I brought in it to say, what are the latency, IOP, and bandwidth gains of PCIe, NVMe versus SAS, for example. SATA is a different story, but for SAS, the answer is it's imperceptible. The reason why you would do NVMe and PCIe in a system is a hardware for a hard drive is for possibly cheaper switching costs for system costs. The latency of a hard disk drive, the seek times in the order of milliseconds, the interface overhead is insignificant compared to the rotational and seek time penalties of a hard disk drive. None. Very imperceptible.
So the question is, how does so SAS has the capability of extending, from maybe even one cabinet to next. I imagine the NVMe has a similar limitation on copper length that it can go before it's terminated. That can actually provide that same kind of connectivity or expansion capabilities with NVMe?
Yeah, so like SAS might be 3 meters, for example. I don't know that answer off the top of my head. It's a similar PHY, so I would expect it to have similar behavior, but right. Yeah.
Back to her question, we should also point out that, although it's not a pure IOPS opportunity for NVMe on hard drives, but when we get into dual LUN situations and so on, that's where there's possibility that over time PCIe presents a better, lower cost, synergistic kind of thing, right? Because the SAS ecosystem is sort of small and contained. It's not really looking like growing, but PCIe ecosystem is got a lot more supplier base and so on. So there might be a better opportunity over time to do dual channel, multi-channel I/O and hard drives with PCIe.
Yeah, there are other benefits to it. Higher queue depth, it has the ability to set up separate queues. You can do prioritization and other, there are niceties to it that are better or more modern than what was conceived of when SAS was designed. So it's not totally without its benefits, but purely from a performance standpoint, there's not a lot.
You have focused on the connectivity. What about the higher level functions like encryption, decryption, and all that? I mean, are they also to be negotiated? Or?
Yeah, that's separate. So the interface NVMe command set for hard drives is being worked on outside of this. This is really just focused on the physical interface between drive and enclosure.
Single port.
Yeah.
There's a pin that tells you to go single ported, or 2x1 versus 1x2.
It's 2x2 versus 1x4 right now as defined, yeah. But we would make it 1x2 versus 2x1.
The other thing is
yeah, spin up is separate than this. That is covered. The NVMe working group is working on the spin up aspect of it, whether drives auto start or not. That's apart from this part. I didn't envision using a signal to burning a pin on that. You could, but I think they'll do that on the interface. Any more questions?
So relative to this concept on a working group, and I think a couple of things were mentioned here, but there's two really big bodies of work that have to be done that really take the community coming together and agreeing to get some sort of standard, right? And the connector is one. The other one is the command spec. And we have an initial proposal. It's not baked yet, but that's one of the reasons why we'd like to get this working group going, because we'd like to kind of bounce those ideas. So basically, our bias is to say, hey, we don't want to go in and create a bunch of new work for NVMe that's specific to HDDs. So our analysis is that we think we can implement within the existing standard largely for hard drives. And so we have we have a matrix that essentially kind of breaks down into a whole bunch of stuff that's coded green, like, okay, we can do this within the command spec, not an issue, and it'll work for a hard drive. And then we have a bunch of stuff that's coded red, which is, it makes no sense to implement this part of the command spec for HDD, right? And then we have some stuff that's yellow, and there's some ambiguity there, right? So all of that really is the basis for some conversation that really has to happen. So we'd really like to, have that conversation about who'd be interested in doing that, and then get some coaching from George and Jason here on how we might kind of coordinate that.
Part of the question always is how are you going to activity tracking with NVMe, PCIe?
Yeah, I think, well, I should also mention one other. Yeah. Yeah. Right. So we chose to come here first because we think that the most likely adopters of this would be cloud, right? And if we go and we try to bring like the traditional IT guys to the table, their bias is going to be a whole bunch of legacy stuff that it's going to overcomplicate this and not make it really usable. So our bias is we want this to basically be a cloud-focused, initiative. Yes, yeah, exactly. That essentially it should look like a slow SSD, right? And so we thought that having the conversation here, getting that agreement with that bias, would then ultimately lead to some other conversations about where to take, for example, maybe the connector goes into some other. Exactly, right. Perhaps, yeah.
Yeah, we're going to not have any impact on the interface. It's really just, and a lot of the stuff in PCIe and NVMe, things like SRIS is optional, for example. So if we said we must be SRIS, we're compliant with what they require. We're just narrower than what they require. Yeah. Yeah. Resets are another thing that they list as optional, but everybody is, it seems to be common right now.
So you guys have any guidance about how we'd take those next steps to just see if there's potential to make that happen?
Absolutely. So we did some of this for the Cloud HDD group, where we got together to discuss the use case and the high-level concepts around that. Maybe that's a similar approach we take here. We do some face-to-face meetings, calls, whatever it takes to discuss the uses, pros and cons of what the request should be. I think the caveat, as Jorge mentioned, is if you start getting down into the standardization, which body, that's probably not the best forum, but the use case, this is a perfect forum to get us all together to debate everything. So I think, exactly.
Where we've gotten into trouble in the past, as OCP, is when we start trying to deliberate on things that will be part of a spec. So for instance, we try to deliberate on NVMe spec, content and material. we get into all the differences in terms of the IP rules for NVMe as an organization versus OCP as an organization, and having to abide by OCP rules and then have contracts and agreements for everyone that participated in the OCP forum to have that transition into an NVMe forum. It involves more lawyers than I usually like to interact with. Has been one of the issues. However, what I do think is a good idea and we can do is more of the use case. It's back to what you're saying. Is there value here? And I think that's what you guys are trying to showcase is, look, it's about connectivity. We see an ecosystem where perhaps a SaaS-based ecosystem doesn't have the same growth potential as a PCIe-based one, and I see some cost, reductions there and maybe commonality in platform. Hey guys, you guys are adopters on the other side. Does this make sense? And then at least get consensus there so the initiatives in your proper places can happen. So there's a balance there. It's just tricky when you start talking about content material and what kind of spec you're going to do. But in terms of the use cases and things like, here's how a chassis that incorporates these devices should look like. Hey, by the way, why don't we jointly design one and make the hardware all available and it's a spec contribution to OCP? Right on. So that discussion is okay. It's when you start getting into the things that should live in other bodies is where we get into trouble.
Yeah, and to elaborate on that further, I mean, the system level trade-offs, we have technology creators in the room, we have system creators in the room. You get us all together, we can start debating the pros and cons. There may be overlap, and we can try to tease that out. It's a good opportunity. We can certainly help set that up. So if people are interested, reach out to Jorge and I. We can, as long as multiple people when it comes to the table, then it's good. If you have 2 people that show up, then you're probably not getting the desired outcome. Thank you, David. Thank you, John. Appreciate it. Oh, one more question.
When you talk about cloud provider, we need to address that. Are they willing to pay more with this connector without the IOF gain, right? That's the question so that...
Right. I think that's where it bubbles up from a device level to a system level, because there may be trade-offs. You may spend more money on a connector or device to get other benefits at a system level. So I think that's where the system teams can come together and give some guidance. Obviously, in this forum, we're not going to share costs and exact benefits, but we can give directional guidance. This makes sense. We see these type of use cases that could pan out from concepts like this. All right. Do we have Alfie from Inspur in the room? Because up next. All right, up next we have a presentation from Inspur on their Goose Lake JBOD. So you can do the presentation? All right. Q&A, all right.
There we go.
Do you have a laptop for the presentation?
Yeah.
Okay.
On laptop.
Sorry. If I feel like we close the conversation without an action item. So the action item would be, you can send a call for participation on the main list, and then get respondents, and then schedule a date for a kickoff. And then if we get enough, people, then we can talk about formally starting a subgroup. That's like the mechanics of it.
Not yet. Oh, do you have a HDMI port?
I think there isn't. Okay, he can hear you.
Okay. So we can do PPT, right? No.
You need to do that because there are people on the...
Yeah.
So can I leverage a laptop so I can copy my... Yes, I have it.
Okay, we can do that.
Sorry.
And for everyone else who's presenting today, if you have your laptop and the presentation ready, please install the GoToMeeting plugin. That'll enable us to make you the presenter and to share the content both locally as well as on the phone.
Version, PDF and...
That's fine, right?
Is this one working?
Yeah, that's working too.
Hello?
Yep.
All right.
Or actually, I might need your laptop.
Oh,
got one
oh, you want one more? Ah, yeah.
Let me see. You guys, oh, yeah.
Well, remote they won't. So until I make it for something.
Okay. Do you want me to install GoToMeeting on this? You want me to get on?
Yeah.
Okay, hold on. Which one is it? You know which one it is?
That's under bridge 1.
Okay. I'm not connected. Hold on.
Oh, yeah, that's gonna become problematic.
Do you have a Wi-Fi?
Yeah, so yeah.
Okay. I have
No, I only have USB. Here, I'll
okay.
steal your adapter.
Yeah, there you go. Yeah.
Pick your favorite one.
Okay. And it's already got the USB. I was gonna say, if anyone else needs Wi-Fi, let us know in advance. Right. Do you need Wi-Fi? Can you get the Wi-Fi?
Yeah.
Okay.
All right. Is there the first point? All right. All right. All right, everybody. Sorry for the delay. Appreciate the work here. So my name is Han Wang, and I'm an engineering architect in Inspur System US. So since I'm the first time to join this workshop, so I think maybe allow me to introduce myself a little bit. So I used to work in HPE and Dell and HDSD, formerly is IBM Storage Group. So my background is storage and server, so I go through all the storage group and hyperscale enterprise and HPC group. So this is roughly the background on my previous experience. So today I would like to give an overview about the one Inspur JBoss solution. So the code name is called, what can I? All right, yeah. So the code name is called Ghostlight.
Minor technicality point. You had confidential for tonight, but that's just a typo, right?
What?
You don't mean that content will be confidential.
No, not confidential.
Just for the record, this was, okay.
It's internal. Sorry for the confusion. Okay, so very high level background of this box. So this JBoss solution is a 2OU solution which can hold 34 drives totally. So there are two independent, two this tray, which each one take 1 U, and it's a front accessible. In the back of the chassis, there are 2 cable arms to support the cable to each tray, and in the back, we have the 4 dual rotor fans. So in this introduction, I will briefly go through how the system diagram, the mechanical explosion view, and introduce a little bit about the major boards of the chassis, and some system diagram and the power rail, and some management. Okay, so this is the front view of the box. So you can see very clearly we have 2 identical the storage tray. So we have the ARC link port using mini-SAS link port, and we have a UART port, management port, and we also have a downstream port. So in the back, from the back view, so we have 2 8056 fans provide cooling. So we use the bus clip for the powering to the box. So this is the mechanical explosion view. So so basically we have 2 major boards. So the front is the expander board backplane. So it has the expander chip. So this is the middle the hard backplane. So we also have the fan controller board, which is taking out the fan control and routing the power to the front 2 boards. So for this front expander board, so we have 8 connectors, which allow connecting 8 drives. So these 2 boards, expander board to the middle hard disk plane backplane is using the edge connector. So for this HDD backplane, so we have 9 connectors, which allow us to have 9 extra drives. So total this connection from this expander, we can support up to 17. So this is for 1 tray. Since we have 2 trays, so the total in 2 U form factor, we can support up to 34. So this is the top view, so nothing special here. So you might have a close look at. So this is our expander chip, and we have the 3 mini cells for the uplink or for the scale out. So we also have a management port and provide onboard management, also debug and the firmware. I can talk about later. Also, we have extra mini-SAS connector can allow the downstream connect to other box. So this is a split out of the 2 trays. So basically, the information here delivered is so there's a 2 tray totally separate, and has their own the cable arm, and they share identical the fan control board, which provide the fan control. All right. So this is power topology. So as I just said, the fan control board also provides the power distribution. So it will go through the HDD backplane first. So it will feed the 12 volt standby and 5 volts and 12 volt main power to the 9 drive here. And the power rail will go through the edge connector and feed to the expander backplane board. So the 12 volt standby will go through the DC conversion to the 3.6 standby to the onboard CPLD. And also the main power rail will deliver to A drive, we already talked about, and also the DC conversion. And this is expander chip. Yeah, this is roughly diagram of how the power rail feeding. So this is the expander board diagram. So the chipset is using PM8054 chipset, so which you can support 36 12 gig SAS port. So we will see, so there are 8 SAS lanes has been shared to the HDD drive, and we will backfeed the 9 SAS lane to the HDD backplane. Also the RAS SAS lanes will use 4 mini SAS HD to allow the 2 multiple hosts and also scale up, also downstream. This is a mechanical top view of close look of the expand board. So we have the 8 connector here, nothing special. So this 2 area can host 2 drives. This is our expander chip and the mini SAS board, management board, and the extension connector, which we can connect into an expander management board. So this is the top view of fan control board, nothing special here. This is the fan control and power distribution, and might have some fan failure LED. So the reason we have 2 separate boards is, so this is the modular design, so we are leverage this backplane board for other platforms. So that's why we put the 2 pieces. So we use the edge connector to allow the power and management to go through the edge connector to the front expander card. Okay, so this is, it's on board on top, sit on top of the expander. Basically, it's an expander management board. So we have our dedicated port to allow we can monitor all the expander status, do the management telemetry, also can update the firmware. So I think that's pretty much about this box. So thank you for your time. Any questions? Yeah.
How do you monitor the health status on the HDD?
The health status. I don't know the detailed design. So I think
the green and the red. How do you define the red?
I don't have the very detailed design information, but I can take this offline. Yeah. This is just a high-level introduction of the JBoss solution. So we will provide the spec. So if you want to look at the detailed diagram, also the feature implementation, so please don't be hesitant to contact me. Yeah.
Do we have any other questions in the room?
I'd like to say whether they share the same issue that other presenter provided. So do you share the same issue, like the reference class or the connector, which John was talking about? I think John was the previous presenter, right?
Question about ref clocks.
Can I request you to repeat your question?
The issue that John was talking about, are you taking the ref clock locally, or you can take from the
yeah. They're both. Yeah.
But just make it
PCIe bus?
Yeah, you had the PCIe connected to SAS.
I think the question was your edge card. Use the by 16 edge card.
Oh, okay. I saw different. Oh, okay. All right. Sounds great. Any question or comments? Otherwise, I will hand it over to the next one. Okay.
All right, perfect.
All right, thank you.
All right, thank you. And next up, we have Matt Ninesling from Spectralogic. He's going to talk about some future tape drive interfaces.
Just one final question. What's your plan
plan for this? Is this something you're planning to experience OCP or spec or design? What are your...
We already we're planning to, we're working on the spec documentation. So once we have that, as in the works, and we will circulate that for comment.
So a specification, but what about the program?
That, yeah, right. Yeah, either Inspire or accept it. That is something. Yeah, right. So the first thing is to circulate the specification for comment, and then once that is approved, then we'll try to build the design.
Okay. It would be good if you can compare and contrast with some of the existing designs. Okay. So there are a couple of existing designs today in the OCP storage project. And it's good to compare and contrast and say, hey, here are the things that this brings to the table that you don't already have. So, because these are things that are going to be asked of you. Yep. Awesome. Thanks.
Sure. Cool. All right. So I'm going to talk about tape drives and tape libraries and interfaces to them. I wanted to start out with, hang on, with just a little bit of a history on tape stuff. So tape started out, 10, 15 years ago, we were using SCSI pretty much as the only interface for tape drives. There was HD and SD and LVD and all these different versions of SCSI. Eventually, data centers moved to a fiber channel interface and adopted a SAN to connect all the different devices together. Initially, there were no tape drives that had a native fiber channel interface, so a lot of tape library vendors, Spectralogic was one of those, developed bridges. So you had fiber channel come into a bridge, you'd branch out to X number of SCSI tape devices. Eventually, tape drives did introduce a fiber channel interface natively, and now that's what everybody pretty much uses. Over time, SAS was also introduced to tape, and that became more of a modern, within a rack type of an interface to connect up multiple tape drives. But it didn't work outside of, a rack or maybe two racks. So everyone was still stuck with fiber channel for very large archive situations. During that same time, over the last decade or so, most modern data centers have switched to an entire large high-speed Ethernet backbone. So today you're going to see, maybe a 400 gig Ethernet backbone, 100 gig to racks, 2550 within a rack, that kind of thing between different devices. Tape doesn't really fit into that very well today. We're still fiber, we're still this thing over on the, the side of the data center that is a SAN, and it requires fiber channel HBAs, requires, special people to administer them. It doesn't really meet, fit into a modern data center near as well. So really, there are quite a few benefits. I think everybody that's used any kind of modern storage devices realizes that Ethernet is where everything has gone to. Maybe not within a chassis, but at least within a larger system. That roadmap is moving very quickly compared to a lot of the other interface roadmaps. So if you look at SAS, fiber channel, any of these other more legacy interfaces, the roadmap is much slower from a speed perspective. So you'll see, there's already 400 gig out there. 2540 is 50 is very, very common. 10 gig is just built into chips now. You basically get it for free. It's also, it's very similar kind of to what Seagate talked about earlier from a NVMe standpoint with hard drives, in that it's a lot cheaper from an overall infrastructure standpoint. Switches, cabling, all that stuff just works much better if you're using Ethernet, as well as just the people to use them. So right now, I've worked with a lot of different customers over the last year, and there is a big push to try to figure out some way to move away from fiber, but there aren't really many adopters yet. So there are some options out there. With the IBM Enterprise tape drives, the 1155 and 1160E drives, they do now have a native 10 or 25 gig interface to the drive itself. and it is strictly RoCE that you can use to interface with those drives. RoCE is a very high-speed, low-latency modern interface. It is still kind of nichey, though. It hasn't caught on that much. It's not used that widely, especially on this type of storage. The advantages really of RoCE are you're talking to the memory on the device that you're interacting with. So there's very little CPU overhead. It's almost negligible from a server CPU standpoint, which is a big advantage over things like iSCSI, which have been used historically on Ethernet interfaces to storage devices. It's also very high bandwidth. None of these things are going to make the tape drive itself go faster. It's still going to have its throughput. You know, with an 1160 drive, you're going to get 400 megabytes a second throughput. But you can drive a whole lot of different drives from an individual, switch or an individual HBA in a server with one of these more modern interfaces. The downside is there are no LTO tape drives out there right now. So that have Ethernet interfaces. Right now, it's either fiber or SAS. And that's really where the bulk of tape is in the industry, is LTO. So there are certain users that use TS. We see a lot of that in HPC, some in banking, a little bit in the cloud maybe. But the majority of tape drives shipped per year are all LTO. And there's really, there's no adoption there at all. So, and there's no real roadmap currently for Ethernet LTO drive as well. So really what I'm looking for from the OCP group is is there a way to gauge, is there enough interest out there to really push a different interface for tape? Tape is really being used more for just true archive storage at this point. It's not, disk, flash, all these much faster, more, different storage devices are used on the front end. But if you want to store hundreds and hundreds of petabytes, that's still where tape really fits well, but it doesn't really fit into a lot of the environments as well anymore because it's an older technology. It doesn't have as much of the newer connections and that kind of stuff as it should. So the downside is that no one's really adopted RoCE. We've shipped a couple of libraries that they're mostly used as test systems and beta customers that do have RoCE drives in them, and those customers are gauging whether they want to use that long term or not. There's a little bit of use in different, some other, maybe a little bit in the cloud. People are playing with it, a couple other places, but it isn't widely accepted. The drive shipment numbers are very, very low. And yet everybody says that that's what they want. Nobody's really willing to be the first, the first guys to really adopt it or buy into it. It's also difficult to use right now. With the TS RoCE drives, it's the environment it can work in is very small. You have to use a certain OS, you have to use a certain driver, you have to use a certain HBA. It's not something where it's widely adopted. There's a large matrix of, different components and different OSs, different drivers that work with it. And I don't know if, what I think it needs is some group to really buy into it more and drive some of that adoption or drive some of that utilization of those, different ways to make people more comfortable with using it. And that's really it'd be a benefit for tape long term. Just as an industry, if we could get it to fit into some of those more modern situations better. So that's really what I'm looking for from OCP, if there's a way to drive some of that or not. Yeah.
So,
and we don't do tape drives, right? We do tape libraries at Spectra, but we have played a lot with different servers, different bridges, different ways you could connect Ethernet to tape drives, mostly SAS. And we're using a lot of different, we've played with a little bit with, we've played a lot with RoCE on that, a little bit with iSCSI. RoCE is great from a throughput and overhead perspective. You can push a lot of data. You can see 90 to 95% at least of the throughput of like a 50 gig NIC with RoCE, whereas if you put iSCSI on there, you're going to see 60%, and then you're going to run out of juice at that point. So there's a lot of bang for the buck there. It's just nobody's using it yet.
My name is Tim Walker from Seagate.
Yeah.
I think you might have answered my question already, because like an NVMe over Fabrics, which initially rolled out in a RDMA infrastructure, but we're seeing a lot of talk, a lot of excitement about the NVMe over TCP, because the infrastructure, to maintain the lossless RDMA infrastructure requires expensive, like you just said.
Yep.
It requires talented people, expensive equipment, and a lot of luck. So does it take? And the logic behind it is that the majority, the large percentage of storage workloads, the differences in latency and throughput between RDMA and TCP/IP really don't impact the application much. And so, what about you?
It's not really that the overhead affects it that much. It's that how many different devices can you push from that single server, from that single HBA that you're using. So if we were to hook up, a bunch of tape drives that are all running 300 or 400 megabytes a second over iSCSI, we'd have to have 2 or 3 different HBAs for say 24 tape drives. Whereas with RoCE, you can get away with one, two ports basically, 250 gig ports.
So like iSCSI and RoCE is like, two opposite ends of
right.
A way to move block-oriented data over Ethernet, right? So
it is, but those are kind of the only two that have ever really been utilized with tape at all, or with that storage device. There are definitely outside of that, there's lots of other ways to do it. That's all that's really ever been used from a tape perspective. Not saying that, and that's part of the idea is there something better, right? If you weren't going to do RD or RoCE, you could look at, some other more, lossless protocol that's not going to have much CPU overhead or anything like that associated with it.
Any other questions?
So this talk is mainly focused on tape only. Are you considering like a tape with some fast storage builder or?
That's more of a tiers of storage kind of a thing. It's not really. It wouldn't be just with tape. You wouldn't have fast storage in a tape drive itself. No. You may have a whole bunch of fast storage in front of a tape and cache stuff there, and then move it to tape after that.
Yeah, so I'm thinking just like a whole giant storage multi-layer, because you talk about lower latency. As we know, the tape robots like overhead majorly is like seeking the right tape drive and put it into.
And it's not as much the latency that hurts. It's all the overhead associated with a different protocol. Something like iSCSI, there's a lot more overhead with every single packet that goes across. So you just don't get the same amount of throughput from the same speeds that you're pushing from a server. Because a lot of it is just overhead. It's not really a latency thing. It's just you can't push as much data over the wire at the same time because there's so much other stuff associated with the data.
All right.
One couple more in the back.
Hey Matt, I think from the at scale, definitely the Ethernet really helps a lot, simplify a lot of the challenges with the infrastructure.
Yep.
But one thing is like, do you have any thoughts on the RoCE or the RDMA over Ethernet? So RDMA has a lot of vulnerabilities with security. So do you have any thoughts on that? Like or have you looked at it, like how to mitigate those or?
So I think some of our assumption is that you're secure in front of that. The assumption is that there would be security in front of where your RoCE is. So you would have lots of firewalls and lots of other things before it gets to the transition between your disk and your tape. I don't think we see this being on the other side of that security wall.
Because one of the advantages with point-to-point topology, like with fiber channels, you can have you can separate your network and your data or the direct attached storage.
Yep. And you can still do this with that, right? You could have dedicated servers with a 25 or 50 gig HBA in it, and you could have a switch in between that and the tape library and drive it all from that and not have it be on your general network if you wanted to. But, I doubt you guys have much fiber channel in your data centers today unless you have some tape there, would be my guess.
But I think what he's bringing home, though, is when we switch from, let's say, the legacy fiber channel to an Ethernet, if you're still putting in that secondary network, you're not getting all the benefits that you really get out of it. You get some, but not all.
Yeah.
Obviously, moving to a true Ethernet across the board certainly has benefits. The RDMA aspect certainly add some challenges to it, especially at scale. As was mentioned, I mean, you go from hundreds of thousands of nodes, you get those working, but when you have hundreds of thousands of nodes, it's a much bigger challenge to get working.
If we haven't seen many instances where you have hundreds of thousands of nodes of tape. And this may be more specific to the tape piece where you'd use RoCE, at least initially. It just works well for that high throughput streaming type of a device once you get it going.
So down there.
Matt, just a couple questions real quick. Spectre has been known for building interfaces to bridge technology to the tape. Is that something you're considering with LTO?
It is.
Okay. And then have you talked with IBM about their plans for the LTO?
And that's really a question for IBM.
I know you got a consortium.
It's not, you know, Spectre's not part of the LTO consortium, and we don't really drive what's going to happen with future generations. We do talk to IBM a lot. I think that there's definitely some interest out there in having an Ethernet version of an LTO drive. I don't think there's any guarantees that it'll happen on the next generation.
I think that's the benefit of the people in this room and that can participate in OCP, because if we all say this is the this is the interface of the future, this is where we want to go, and all of our cloud scale data centers are Ethernet based, not fiber channel. Once we start pushing that into the general industry, obviously we're a small portion of that market now, but as time goes on, getting all our voices together and saying this is what we're looking for. Is it Ethernet? Is it RoCE? Is it routable? There are a lot of considerations.
And if it, you know, V2 is, you have to have a DCB switch, but those are pretty common now. The cloud is probably the right early adopter for this kind of a technology based on the scale to fit well anyway.
I think the benefit of bringing this conversation to this room now is to get other people who may have seen this, been on the sidelines saying, this is a really cool technology, where do I start? I think that's where we can start sharing some learnings, lessons learned, and ideas for the future. So
I think that's what we're hoping to get out of it.
Any other
Same question that in the beginning somebody said, why did you not mention the fabric, NVMe over fabric? Are there some issues that you see that why you are not including in your?
I don't think it would really make sense on the tape drive as much to do an NVMe over fabric interface. Maybe someday.
That's the thing with this drive. And allow me to find my soapboxes for a few seconds. NVMe for these lower speed devices, it's not about latency. Because, like we already talked about, the NVMe hard drive that, you know, people talk about and looking at, they don't run any faster because they have the NVMe interface, even PCIe. The advantages to going with the NVMe is, first of all, the standardization, that you now are on the same wavelength as the rest of the storage industry. The fact that they transport, there's a nice clean division between the protocol and the transport, does not exist for SATA and is wobbly on SAS. And the structure of the NVMe command set is flexible and extensible. And so there actually is a number of good reasons to consider NVMe for reasons besides, you know, the microsecond latency where we need to get rid of the locks in the stack. In other words, you know, to take advantage of the microsecond latencies of SSDs and the number of IOPS and stuff. There are lots of good reasons to consider the NVMe command set for low speed devices. Okay.
Yeah. And obviously for tape, latency is not the issue. We have minutes of latency to even get the tape to a tape drive, right? So that's not what we're looking for. It's the commonality of having the right infrastructure that you fit into better.
So if you want your tape library to participate in cloud providers' storage automation, then you've got to be on NVMe.
Got to use NVMe. All right.
That's why I meant NVMe was fabric over Ethernet. The command.
Yeah.
Any other questions for Matt? All right. Thank you, Matt. So we're running ahead of schedule. So we're going to take a break, and thank you, Seagate, for providing all the snacks and beverages outside. When we come back, we're going to talk about a few interesting things. We've been talking about this fast fail in the Cloud HDD group. Many people have heard about it. We'd actually like to cover what we were doing, what the problem statement was. So Lawrence will do the readout from our subgroup. And then after that, WD is going to give us a readout of where this is going in the standards committee. So as we're starting to go from concept problem statement to how do we actually make this thing real and get it out there for others to adopt. So it's 2:18 right now. Let's reconvene around 2:45 and we'll get started. Thank you, everyone. Ed, it's all yours.
Thanks. So I wanted to, after we talked, Jason, several times, I got thinking that I was wondering why it was more difficult to talk about tape other than just removable media. And I believe that some of it comes from the background. So I wanted to spend a few charts on just kind of a level set or getting to the same point on perspective. And the main point can be netted out as tape drives fundamental value proposition of how they were developed, how they were architecture, how they have evolved, has traditionally been max for a backup application, where in a backup application, the most important thing is to get the data to the tape with quality and not ab-end the job. Ab-ending the backup job is a bad thing because the backup doesn't get done. It might not fit in the window, all that kind of stuff. Or capturing seismic shots. You got to get the data to tape. Back when they were actually putting data directly to tape on chips, now it's a solid state. But so the format was designed and evolved into essentially optimizing the probability of getting the successful write, even with variable quality media or variable debris hits and things like that. And likewise on reading data from tape, it was to read the data no matter what. And we would go into what we call heroic actions at times. That's why a lot of tape applications have 20-minute timeouts, because it's not unheard of for a tape drive to crunch on a tape for 10 or 15 minutes before it finally can get the data back by going through a whole successive layers of ERPs. So that the kind of fundamental format things is that it is a multi-channel data flow with an ECC. Essentially, it's got an erasure coding engine inside, spreading data across tracks and down tracks, and it's all real time in silicon. And it allows you to do a couple things. It allows you to read compromised data, which is great from a data reliability point of view, but it also masks small changes in device reliability or degradation, because that's the purpose of the ECC, is to correct it. And since we correct it real time, you don't really see it even in bandwidth. So it somewhat complicates trying to find small changes in performance. Also, it allows you to have read after write real time, running it through the ECC engine, so that as you write, you can assess the quality of the written data. That plus the fact that our fundamental format is a variable block streaming format, where we can rewrite data downstream if it doesn't meet the criteria for the quality of written data. It's kind of like internet, you just keep sending packets till you get one right, which is great for protecting the quality of data written to tape when you do have a variable media environment. But again, it complicates assessing differences between, what if it's not good, is it because of media defects, transient defects, marginal drive, marginal media. That robustness, if you will, also makes it hard to find the differences. And the other thing is that because it is a multi-channel device, but also has other dimensions like tape tension, tape head interface, we will do sometimes, you can offset the servo and get some tracks and not the others, and then come back and offset it the other way and get the other tracks. So it's more dimensions of things to try, or variables that affect the successful operation, as well as just transient stuff. Like I was saying before, you can have a transient bit of debris coming through the HTI. All that means that we have this really extensive ERP recovery system, where it will go way deep in different variables, exercising different things in different ways in attempts to recover data. And again, that's great from a data reliability point of view, but it makes it really hard to start getting in and tracking small changes in performance or understanding why did it do what it did. So kind of in net, the goodness of a tape drive from a point of view of always making sure data gets to tape and can be read somewhat also masks or makes it more difficult to find simple trends in performance degradation, at least compared to say like an HDD where it's single channel device with a single HDI that is, well, say probably more applicable or more an easier system to try to predict failure versus a variable like temperature. So anyway, I'll stop there and see if there's any specific questions or comments before I move on. Okay, so what we would like to do, and what we've talked about here, is come up with feedback from the drive or a means of getting information from the drive that we can evolve into providing what you need in a hyperscale environment that will be the same for everybody and for every client. And so we kind of broke it into 3 phases. And one phase is what tape application should be doing today, what is simple. And the simple thing is monitor capacity, monitor the time it takes to read or write. It turns out that this is by far the highest value and gets you the most information for the least effort because of the way a tape drive operates and the level of complexity in its ERPs and the fact that if it's having trouble writing, it will skip and write the data again down track. You can see effects of degradation at a macro level in either an impact in time to complete an operation or perhaps you're not getting the full capacity of the cartridge. It's easiest to do, of course, at a complete cartridge rewrite, but it can also be done in smaller operations. So many of our large-scale clients who monitor their tape systems carefully, think, places like CERN or whatever, this is one of the key things they always track, and we end up talking to each other about. And then the other thing is there are tape alerts, and I sent you a Word doc that has the details of this stuff and where they are and what I kind of wanted to be the working document as we go forward, just as a starting place. Tape alerts have been used extensively by traditional tape applications for as long as I've been around. And it's also the primary means that tape automation systems use to monitor the drive health. So they are fairly robust and fairly reliable in terms of used a lot, and we have confidence that they provide good insight to what the tape drive is doing. Any questions on that? All right, then the next step would be what we kind of broke into what we were calling phase 1, which was what can be pulled from the drive today. And there are 3 log pages or sets of log pages, ball stats, static capacity, and error recovery log pages, which I like to say basically you can consider them the kind of Darwinian aggregation of all the things that some engineer or customer thought was important to understanding tape health over the last 20-something plus years. Now, there's much more in these log pages than what we've put into this document, but these are the things which we have confidence are are reasonably accurate and reliable. There may be some things in these log pages that were important back in 35, 90 days that hasn't been touched since then. So we can't say that every value in these log pages may necessarily be valid, but the ones that we document in the tape health monitoring Word doc, we believe are accurate and valuable. So we would say we should start looking for statistical trends across the drive and the media population using these. And that's really where we wanted to end up, whether you call it phase 1, phase 2, or whatever. But I think that in the hyperscale environment, we will probably be able to learn more than what we have been able to do ourselves or from our traditional customers. And by looking at trends across a large population, and most importantly, looking for the high nail, the thing that sticks out, either this media is always different no matter what drive it is in, or this drive is always different no matter what media is in it. Those are the things we think that will be most valuable to generate trends. And then what we'd like to do is work with everyone to come up with whatever we find is best, and then adapt these log pages to put that information into there, whatever it is. We don't want to come up with proprietary or unique things for each client. We want to come up with a single set of content or log pages that meets everyone's needs. So, Jason, that was the net of it. I sent you the Word doc that we can post and use for the beginning of the discussion. As I said, I would have something. I'm not sure it's satisfying, but it's the starting point, we think.
Awesome, thanks, Ed. For other context for everyone else in the room, we've had these questions in the subgroup of where do we go next? What do we log? What do we do with that data? So Ed was kind enough to start putting some of that together of what's out there today, and then how do we move forward and next steps, and what else should we care about? Because traditionally, people keep these in well-controlled data centers. When you talk about the hyperscale, we may have adiabatic data centers, and we run even our standard data centers in wider ranges. So we have a lot of questions on, is this media going to live for 5, 10, 15 years? I want to make sure that it's going to happen, because we're no longer talking, hundreds, if not thousands of tape cartridges. We can be in the volumes of hundreds of thousands or even millions of tape cartridges. So as the scale of tape in the hyperscale environment changes, we have a lot more questions and trying to figure out how do we get to the bottom of media reliability up front before we've committed a lot of data to that. Ed, I think we had one question from Sumit in the room.
Yep. Hey, Ed, thank you for sharing this proposal. So I have a couple of questions actually. One is, so do you have any thoughts on we collect the data, how do we process the data, especially in phase 0, you're talking about monitoring the capacity, written, read. So how do we process the data? We can monitor it, but what would be the actions to be taken? Is there any thought on that end? And the other question was, this reference document, is it already on the Google Share or? Not yet. Oh, okay.
Yeah, I wasn't able to post things, but I'll send it to Jason and he can post it. As far as your first, I'm not quite sure what you're talking about, but the starting point would be, how much data you're writing, when you started it, when it finished. And at that level, that's a system thing. I mean, it would also include whether your servers are bottlenecking or something. But our experience with some of the clients in this room have been that's where you can start to see trends just at a very simple level. Like, why are these drives slower writing than those drives when they're in this mode or something like that? Or why does this tape always take longer? Typically, you won't be writing the same tape multiple times, so that may not be applicable in your case. As far as the other data, from the drive, that's where I think we would need a little bit more in-depth discussion with some members on my team, and Kevin Butt is the person I've assigned. I think you know him. In fact, I think he was just with you guys, to be kind of the focal point on what are these values and what do they deliver. I mean, in a perfect world, just suck them up all and we'll do big data analysis and see if anything is trending, if we have that much time and energy. I don't know, did I answer your question, or were you looking for something a bit more specific?
Yeah, I think you answered his question. But then the second part, so what Ed sent to me just a few hours ago, we'll put that on the archive wiki, and there are a bunch of registers and log pages that are of interest. So I think this is probably more for the narrower focused group on the archival side. So for anyone who's interested, if you're not already in that work group, join the mailing list and get involved with that. I mean, it's probably a little too detailed for this audience here. I mean, if you're not familiar with tape libraries, you don't study registers on a daily basis. I don't know how many of us do, but it's probably not the best topic for here.
Yeah, I agree. That's why I wanted to put it there. But I think that's the basis where, and again, like I've assigned Kevin Butt, who is our SCSI T10 guy and the person who knows the details of this, and we could talk to you individually through our normal relationships about those fields if you have questions.
Thanks, Ed. Do you have any more slides, or is this the last one?
That was it.
All right. Thank you, Ed.
Like I said, I didn't want to go into SCSI commands and something like this, both because it's boring and I don't know it well enough.
Perfect. All right. Thanks.
Thank you.
Now we're going to pivot over to fast fail, and Lawrence, who is on the call, we'll go through some of what we've been talking about the last 2 years of what the intent was, why we came up with it, and then WD give us an update on how that's going in the standards body. So Lawrence, are you ready to be a presenter? Lawrence, are you able to hear us? Oh, there we go.
Yep, and can people see my screen?
Yes, we see your screen and hear you.
Awesome, all right. Hi everyone, sorry I cannot join in person. There are too many things going on, too many fire. So this is a fast fail read. As Jason has mentioned, this is something that we proposed into OCP for us to work together on almost 2 years ago, and we're pretty much there. So basically, we got the spec. We were able to reach consensus and actually got the spec written out. And it was presented to the OCP IC a few weeks ago. And I think Jason, as of yesterday, I did not realize this, but enough people have voted that we actually got more than 50% vote yes. So basically, this is now effectively an OCP spec, an official OCP spec. Is that correct? Sorry, I cannot hear you guys, but.
I don't think anybody said anything. This is Doug. I think the vote has to finish and then things happen. So might be a little premature, but I think it's coming.
Okay. Got it. Okay. So I shouldn't jump to conclusion yet. But basically, yep, people are still voting.
Yeah. Can you guys hear me?
Yes.
So it has passed, and Michael will be uploading it to the contribution database, and you should be able to access the spec shortly.
Great, thank you. Yeah, because I know that on the T10 and T13 side, people were looking forward to reference this, the OCP spec, because that's the one with all the community feedback. So I know that people have been wanting to reference that for quite some time. So awesome. All right, and this presentation basically is a summary of what the spec covered, the intent, the background, and what we think that it actually does. Okay, and please feel free to interrupt me in between if there's any question. So this is, by the way, the presentation was presented to the OCP IC, the incubation committee. Okay, So first of all, the fast fail read spec is developed under the JDA, the OCP JDA. This is a new framework where we're hoping that all the future Cloud HDD initiatives, Cloud HDD related specs can actually follow this process. So if you follow that wiki link, you can learn a lot more about that whole initiative, the process, and so on. We're hoping to have even more Cloud HDD specific projects and initiatives, innovations happening in that space in the future. And then in terms of this particular spec, the fast fail read spec, it is jointly written and contributed by all of the companies listed here. Okay. All right, and then moving on, this is the problem statement. So why are we working on this? So HDD can sometimes be slow to read. Okay, so I threw out an example over here that at the long tail, such as 99.9 percentile, that means 1 in every 1,000 reads, the read may take a while. It may take, say, on the order of 500 milliseconds or half a second. Okay, for so yeah, okay. And usually, sometimes some people are okay with that behavior. Some people are not happy about that behavior, right? And the question here is, in cloud, we can actually do better, right? Because when people actually have a single hard disk in their desktop system, they may say, hey, sometimes my computer is acting up a little bit because it's 1 in every 1,000 times. But as soon as the computer resumes, they're like, okay, fine, things are working again. But in the cloud, we're asking, how can we do better? Well, how cloud does better is that because we have a large distributed file system, data is stored on more than one HDD. So what actually happens in cloud is that when one HDD is too slow to read, we can just read from another HDD. So in this picture on the right, basically we have 2 hard drives. Okay, we have one image file that's stored on 2 hard drives. Those are the 2 red cylinders. A user is trying to access this data. Okay, it turns out that a hard drive on the left is taking too long to access. And so what we can do here is basically the user just needs to access the data from the hard drive on the right. It doesn't need to wait for the data on the left because it's the same piece of data, right? So basically the user will be able to retrieve data from either hard disk. As soon as one of the hard disks can return data, the user has gotten the data and the user is happy. Okay, so that's basically the general behavior. Now, what we would like to do better is, so now we're reading from another disk. That means the user on the right is now reading from a disk on the right. But when this happens, we want the first disk, which is the disk on the left, to free up so that another user can still use that disk. Okay, so in this particular picture over here, the user on the left, okay, so the 2 blue people, the blue person on the left is trying to access the first hard disk, which is the hard disk on the left that was slow for the user on the right. But a lot of times when slow, it's not slow for all the accesses. It might be a localized defect or localized weak data of some kind that's causing the data to be slow to respond. But it doesn't mean that the entire hard disk may actually be slow to respond. So in other words, if the user on the left is trying to access another piece of data stored on the same hard disk, he may be able to get it back really quickly, right? And so what we want to do is to be able to free up that disk. So instead of waiting to return the same file to the user on the right, who has already gotten that file ahead of time, can we just cancel it? Can we drop it? Can we basically fast fail that reaccess and don't worry about it? So that's basically the high level ask. Before I continue, any questions so far? Okay. And so what basically happened here is all the team across all the different company representatives basically came up with this idea. And by the way, this is an image courtesy of Seagate. Seagate was kind enough to actually drew this picture for us based on what we discussed in the forum. So basically what we proposed is say, hey, look, there are timeout values in the hard disk. We can potentially use some of that. There are different mechanisms, but what if we have 2 timeouts? If we have 2 timeouts, then we can really achieve the fast fail behavior. And the next slide, I'll explain later how that is actually accomplished. But the idea here is we're going to have what's called an inactive timeout and an active timeout. So in the picture over here, everything to the left of the vertical dashed line, so that means everything going to the scheduler belongs to the inactive command limit. So what that basically means is these are commands that the hard disk is waiting to execute on. The scheduler is still queuing and waiting to execute on, but has not yet executed. Okay, so we will have an inactive command limit for the scheduler on the left. For the scheduler on the right, we will then have an active command limit. So that basically means the command has started executing, right? Once it has executed, as people know, hard disk is a mechanical device. What that means is that you need to go physically retrieve the data through this mechanical medium. Okay, so there's positioning, there may be position recovery, data transfer, data recovery, data reallocation, and so on. But it is time spent associated with working on an active command. So what we basically want to set here is, okay, if we can have a command limit, a timeout for the thing on the left, and a command limit or a timeout for the thing on the right, then we can specify to a hard drive the exact behavior. And when it's actually taking too long, right? That is, if something is going beyond the command limit or going beyond the timeout, the hard drive should just drop it. That is fast fail. Okay, any questions so far? All right, then moving to the next picture. So now that we have these two timeouts, how do we achieve fast fail? All right, so I try to give one specific example over here. This is the non-queued example, which is the simplest case. So that basically means that when we say non-queue, it basically means that the distributed file system software is not asking the hard drive to do more than one thing at a time. Okay, if there are multiple requests, anything like that, it's all stored in the distributed software itself. The hard drive itself only works on one I/O at a time. Okay, when under that case, which is the simplest case, then given those two queues, what we can do is basically to utilize the active command limit queue only. We don't care about inactive because there's no queuing. Then fast fail can be achieved by setting a very tight active command limit. So in the previous example, in the pictorial example I gave about 500 milliseconds. Let's say if I want the hard drive to only give it time for 50 milliseconds, for example, then I can set an active command limit to 50 milliseconds, right? Then then for most of the time, the 50 millisecond will be sufficient and I'll be able to get back my reads, right? And if it takes longer than that, great, the hard drive will basically stop. Once it goes beyond 50 milliseconds, you'll say, look, I passed my timeout, I'm going to fail this IO read. And if you want to do a normal read, which can sometimes happen either due to management commands, other more important activities, or in the rare cases, hey, I have data on 2 hard drives or multiple hard drives, every single one of these hard drives are slow, I still want to retrieve my data, then I might want to do a normal read. So this is this heroic read where even if it takes 500 milliseconds, please still spend that time because I cannot retrieve my data any other way, right? Then that becomes a normal read where we have a relaxed active command limit. Then the hard drive knows, okay, now I can really take my time to read that piece of data and I need to do the best I can to return that piece of data, even though it takes quite some time, even though it takes 500 milliseconds. So that's how we foresee this interface to be used by the community. Any questions? All right. And this, I believe, is the very first OCP project where we actually have partnership between OCP and the HDD standards industry standards committees, which actually include T10, T13, and SATA I/O. And luckily, in order to achieve this, many of the Cloud HDD fast fail read attendees are also active participants in these standards committees, which is great. And so what we basically agreed upon is that in OCP, because this is the rare forum where the HDD users, not just developers, designers, and manufacturers are in the meeting, but in OCP, we actually have HDD users actually in this meeting. So we were able to actually define a set of standard behaviors between the host to HDD cloud software usage in OCP. And so once that's achieved, then we can basically define the exact API interface behavior in the standards committee, such as T10, T13, and SATA I/O as appropriate. Okay. And finally, I believe this is the last slide. So in terms of OCP participants, what does that mean, right? So based on what people have discussed in the meeting, I believe Seagate, Toshiba, and Western Digital all have expressed interest to enable the fast fail read API, right? Once all of these get standardized in their future HDD products. And I believe Facebook, Google, and Microsoft have also expressed interest based on what we discussed and how it relates to the storage stack to purchase these HDD with fast fail read API enabled and to be able to use these interfaces in the future in the data center. And that's it.
Any questions here in the room?
How about the write operation? Are you going to do the write operation? Are you going to look into the timeout limit as well?
The what timeout limit? Sorry, I missed
the question was, are we going to look at the write timeout limit instead of just the read?
Ah, got it. What we actually discussed is that based on the cloud usage, the write timeout is actually not as important as read. So it's actually not the higher priority. The reason for this is because writes is easy to hide from the user. So in other words, as long as we can guarantee that we do not lose the data, we can put the write in flash, we can put the write in flash as a cache, we can put the write in other media through other ways, having more redundancy, for example, even though it's in DRAM, right? There are many ways to guarantee that writes are good and to tell a user that I have gotten your write, even though it's not yet committed to the physical media, that we will not lose your data. So writes are easier to deal with. Read, on the other hand, is a problem because if I don't have the actual data, I cannot tell the user, I cannot fake the read. So in other words, in order to tell the user I have done your read, I need to deliver the data back. So, unlike write, where I can say I have done the write, but I haven't physically finished the write. So read is the one that's of particular interest here. Does that make sense?
Yes. Any other questions in the room?
Is the proposal to send the timeout with the command or just configure and just decide fast or slow?
Sorry, can you repeat your question? It's breaking up for me again.
Is the proposal to send the timeout per command basis or just configure and just talk about fast or slow read?
The proposal, once you see the detailed spec, actually calls out multiple different implementations. So if I remember correctly, and it's been almost a year now since we finalized the spec, if I remember correctly, I believe a lot of these are tagging on top of how ICC works. So the NCQ ICC type of behavior. So I think there's a way to set it per group, but I think there's even a way to set it per IO command, if I remember correctly. But what I believe happened that we agreed upon is that agreed upon implementation is a superset of what everyone needs. But sorry, it's been a year, so I forgot what the actual upon spec is. I can look it up, but
Yeah, this has been going on for a while, so hopefully Ralph will give us some more updates on where it is now. We completed a lot of these efforts quite a while ago, and it's been waiting to go through the signature state.
Right, the legal signing and getting all the companies to sign all the legal documents was what's been taking the longest. By the way, related to that, we actually have a modification to the Cloud HDD process in the future, right? So for the very next one, the process will change to, we're going to do signature at the beginning. There's no more signing required at the end. So in other words, once the spec is done and everyone has signed off on it, there's no more legal involved. So the legal agreements all happen at the very, very beginning. So you'll cut down the legal agreement time by half. Instead of signing once at the beginning and once at the end, we'll just sign once at the beginning.
Any other questions in the room?
So Lawrence, you mentioned an example with a non-queued case. So yes. If it was a queued case, I assume that the timeout, the command limit for fast fail will be the sum of the inactive and the active. Is that right?
It's actually more complicated than that. In the queued case, what we're actually enabling is for the host to have the capability to individually set inactive and active timeout. And there are reasons why we want to do that. Because in a queued case, what if there's priority? What if we want something to actually trump? What if we want, and so on. Basically, in a queued case, things get a lot more interesting. And that's why we said that, okay, we actually need both command limits. But you're right, the total command time seen from end to end is the sum of these two. That is correct.
Any other questions? All right. Thank you, Lawrence. And now, so now that we've talked about the process and the challenges we were looking to accomplish by working together, Ralph's going to now explain how we've taken these ideas and the high-level concepts and started moving those into standards bodies.
I need.
Your AF2 meeting installed and ready?
Yeah. You want that? Share. Where? I did check the share.
Yeah, we see it on the.
Oh. So
you can still use your laptop. I'll just use it.
Oh, you got a copy?
You are sharing it.
Oh. Ah. I'm going to pass my screen share through his laptop. Yes. Okay. So, is that me again? No. Basically, Joe Brer, who has since retired from WD, was in all the meetings that Lawrence described, and he and Robert Horn put together a way to use an existing SCSI feature to add fast fail support. Okay, and like I said, Joe's retired, and I got to take over making the SCSI changes. So here I am. I'm going to show you what we did with their proposal and how the two inactive and active times are there and that sort of thing. But I also have to point out, a lot of people have asked me why it's command duration limits, so I'll say it now. People got to the part of SCSI that we're using ahead of us, and they called it command duration limits, and they put it in so many places that taking it out is more painful than living with it. So it's called command duration limits because standards do that to you sometimes, okay? I'm going to walk you through the parts about fast fail, but I also have to point out that this is part. That did not work so well. Let's try this. Yeah. This is part of a larger effort that we have going on to try and make HDDs more useful by eliminating the fear of queuing. Because what happens to a lot of people is they look at queuing as a thing that is designed in the drive to maximize IOPS. And from their point of view, that means the disk has developed a mind of its own about what's the most important thing to do, okay? Well, if you've got a bunch of varied clients that you're trying to make happy for a whole bunch of reasons, you can't have the disk having its own mindset, okay? This is where the fear of queuing arises from, and what we're working on in an overall sense is trying to find a way to pass information from the host to the drive so that the host can have a stronger say than just IOPS in the way the queue is working, okay? This work started either at about the time of the fast fail or a little bit before. It turns out that the learning curve is steep. In the last 8 weeks, we've learned that the learning curve is even steeper than we thought. And so that's pretty much what I'm going to say about it. We're still doing that. When you look at the proposal, you'll see parts of this off in the corners, but they're not the parts I want to talk about. Okay? What I'm going to present is our overall proposal, which when the PDF for this presentation is posted, you will find that every last page of the proposal as it exists today, all 20 some odd of them, are in there. And you can see them just the way they're written right now. They will not be written that way by the time they're done because T10 hasn't finished with it yet, okay? But it starts with a page that is an introduction, and you'll notice that in the first paragraph, do I dare try to make it bigger? This did not work well for me the last time I tried it. So, all right. The first paragraph talks about the cloud fast fail. And as soon as I can fill in that first line with a link to a publicly available document, I will do that, and then I will post this as an official T10 document. All right. So that's kind of where we're starting. Come on. This way. From there, we've very carefully not presented the fast fail part of this to T10 so far. There have been 4 documents posted, and every last one of them says, these are the bytes where fast fail is going to go, and there's a link to the fast fail project agreement. Whatever the public document that says fast fail is out there is, that's the link. And we're not saying anything about the fields until here and now. And we're not saying anything about them until now we didn't have the votes to do it. Okay. Now, this is where command duration limits comes from. It's an interesting mess of bits and pieces. In the CDB, there are 3 bits that allow you to define values from 0 to 7, but 0 means do nothing, so it's only kind of interesting. That has to pass through the SCSI architecture model because the last guys who wanted to do this wanted to hook into the queuing mechanism as defined in the SCSI architecture model. The fast fail and the other work that we're doing wants to let the SCSI queuing mechanism go on its merry way and do what it usually does. And so we only have to kind of slide through SAM, but because everybody else did it, that's the way we have to go do it. All right. And another very good reason for not trying to hang on to the SAM queuing model is if you want to do SATA, for example, well, it'll be an entirely different queuing model. So let's just pass everything through and get to the parts that we care about, which are blocks of duration limit descriptors in the case of SCSI inside mode pages that include 2 fields, for example, in this case, fast fail inactive time and fast fail active time. Now, walking through these pieces, this is the CDB. It's a read CDB, and it has 3 bits, but you'll notice one of the bits is up here in this corner, and 2 more of the bits are down there. All right. Among other things, this tells you that the guys who did this work before were the last ones to come up to the table and do anything, because they've actually used up all the bits that are available to anybody in this CDB, and they had to come up with this extra table that's at the bottom of the screen to translate their 3 bits from hither, thither, and yon into 3 bits that make a value from 0 to 7. Okay? But this gets you to a mode page in SCSI, and you'll notice that at the bottom of the screen there are the first descriptor, the second descriptor, and the 7th descriptor, with the ones in the middle being ellipses. Okay? Going with these is something called a log page, wherein there are counters. And you'll notice that we have number of inactive command target misses, okay? Which means that every time a command misses its inactive fast fail target, this counter gets ticked. One way of looking at this picture in a very large scale sense is you have these sets of inputs that are telling the device you want to do something, and on the other side you have these sets of counters that tell you what the device did. But the device's goal in the middle is to minimize those counters. Okay? There are a whole bunch of talks about the algorithms that you can do to accomplish this, but if you look at it from a big picture point of view, that makes it a lot simpler. So I've given you the quickie tour of the crazy quilt path through a bunch of commands and the SCSI architecture model, and I've showed you the log counters, which are essentially the other end of the equation. So now we get to the beef, such as it is. And here you see at the top, in a place that used to be reserved bytes, we have a fast fail inactive time and a fast fail active time. And we have policy statements about what to do if those times aren't met. All right? So hopefully this is partially answering your question. Okay? The CDB has 3 bits. It picks one of these descriptors. Previous to the command being sent, that descriptor that got picked has code values for these, times and what to do, and those apply to that command. Okay? And if you look at the whole situation in SATA, I believe it's also 3 bits you get to play with, and there will probably be descriptors that look a lot like this doing the same thing. Okay. The details of the fails essentially look like this. There's a well, never mind, I was just actually timing that command, let it finish running, and then there are 2 variations for what you do with the data, essentially, when you kick the command out.
That code 0 is basically,
Hmm?
use the measurement to see where you're starting. That's the purpose, is to get a snap, you set your categories up, put them in 0, and just see where you are.
That is, okay, the question was, is category 0 there to be for a setup kind of thing? And certainly that is one use of it. Okay, as a standards wonk, I don't like to nail it down that hard. It's there. If you figure out a way to use it, use it. Okay, if you figure out another code that will help you do something, let me know. We'll figure out how to put it in. Okay, the standard is a tool that helps people do things. It's not, I mean, it looks like a set of rules that it helps the people who write the firmware do their job, but if it doesn't help the people who use the firmware, who use the drives, get the information or the use out of them that they want, then more needs to be done somewhere. And that's my view of standards as a general rule. Okay? I actually think I'm to the question and answer part, which probably means I'm running ahead of schedule too. So, questions? More questions?
Any questions in the room?
People tend to want to know when this is going to make it past the T10 process. And like I said, as soon as the document is posted for fast fail read and I can reference it, I will post this document, which is clearly ready to go for that stuff. And then it will go into committee. One of the value propositions of doing all this stuff without fast fail edit was to allow us to get through that whole path through the command and the SAM and over to the mode page. And believe it or not, the first 3 revisions of the proposal all had changes in the SCSI architecture model part of the proposal. So it hopefully will allow us to get to approval faster by having done this, but I'm thinking that approval is summertime probably. Okay.
Any questions online? In the room? Yep. Jorge?
I don't know why I'm asking these questions here. In the group, but
it just hit you.
So everyone that was participating in the fast fail OCP work group has been through this document? Or it was made available to them? Sorry, that's a more fair question.
Well, the document is the document as it stands today, without fast fail in it, has been available to the public since last.
No. I'm talking about this one that has a fast fail that you have been waiting for the link in order to post it on T10.
Right.
Has that been reviewed within the fast fail OCP work group?
No, it's not.
Okay.
Okay. And in fact, what I heard today makes me a little bit worried about the inactive time, because what Lawrence said about inactive time is not consistent with the definition that's here. It's this paragraph. Is that the one? This paragraph, but the gist of that paragraph is that the inactive time is the time from when the command becomes known to the disk until the first time the command has a chance to start moving the heads. Okay? And whether the command actually starts moving the heads at that point or not is not something that I can get in and reach to. I can only get to the first point where the command has a chance to move the heads.
Okay, so you're going to post this within the T10 so that the committee can start looking at it and normal deliberation.
Yeah, except that the way T10 operates, stuff within the committee is also available to the public.
No, absolutely, yeah, that I understand. Now, next question is, does there exist a version of this for T13, or is it the expectations that will ensue in some time frame? Do you have a timeline plan for that?
You catch me looking not my absolute best there, Jorge. Okay. When it comes to T13, there are people in the world who understand the details of that particular protocol multiple times better than I do. Okay. T10 protocol, I was an editor of SAM at one point. I was an editor of the SCSI primary command. You know, I watched all these pieces. I know that path. So I've been allowing the people who know better a chance to come through and do it.
For that version. No, I'm okay.
And they have equally well been waiting for the posting of the document. I don't know how fast they're going to move after the document is posted, but it is possible that within 2 weeks of the posting of the document, there'll be a T13 document too.
I see.
Okay.
So we do have a mapping of the response to T13 also. It's just not in a formalized form.
Well, we have a bunch of ideas, and rest assured that if the document doesn't appear fast enough, then WD is going to write a proposal.
That's all fine.
So,
I don't care.
So, that it turns out that when you deal with the queue part of T13, you're dealing with a very much more brittle queue than a SCSI queue. In the T13 queue, if one command gets an error, all the commands in the queue go away at the same time. And a fair amount of expertise is required to figure out how to dance around that one.
Now I haven't looked this in a bit myself, but does it still mean that you still have to go to SAT.io and then there's T13 and negotiate all the queuing stuff still, did it merge? I don't even know anymore.
No. Well, it depends, Jorge. It depends on how you look at it. Yes, SATA.io may need to be involved, but it turns out that the same person chairs both SATA.io Digital and T13. So he's not going to get into, either that he's schizophrenic or he's not going to get into a big fight with himself. Okay.
I see. So he can help write the document.
And in fact, he's the guy I'm hoping will write the document.
That would be very nice.
Okay. It will be better for everybody if somebody who knows what they're doing starts this and we don't have to flounder around for a while. So.
Okay.
Yes.
So your approach of, building this table of performance limits, I guess, or command limits, and then the command choosing
an entry in that table that applies to that command. The guy who's doing the system, the storage system software, who is addressing the problem of, we've got multiple requests out to multiple devices. We don't need them all to answer. And if someone is late, he needs to give up.
Mm-hmm.
That basic premise that we started with. Does the guy who's doing the NVMe, who has the same issue on NVMe, is he going to be able to do? Does the architecture of your approach match how NVMe is going to handle this?
I think you just brought up yet another reason why we decided to stay out of the SCSI scheduling model, so that we wouldn't get in the middle of NVMe. And I have seen, and probably can't say any more than that about it, I have seen similar pictures to this one for NVMe.
It would be nice if the industry did it one way. I mean, I'm not saying the command sets are, fully orthogonal, but
no, you're absolutely.
Conceptually, it should be one way to address this one problem. There's common cause.
Yep.
The different approaches.
Actually, you caused me, however, to look at an interesting piece of this. Those times are qualified by this table of multipliers, okay, because the times are not big enough to take a range. And I believe we recently added the 500 nanosecond number specifically to be sure that we could cover SSD cases. Okay, so, and then we added the number and they said, wait a minute, you're not using the digits right anymore. We had to redo the whole table. If you don't enjoy doing this work, you shouldn't try. But other than that, it's a lot of fun.
Any other questions? Going on?
Hello? So I want to echo what Jorge just said. So thanks for bringing this up. Yep. I think it would be really great to share this document with the fast-fail OCP mailing list so that people have a chance to review this. I think in particular, basically, for all the HDD users to make sure that what's being proposed here in T10 reflect their understanding or intent of what's basically written in the OCP joint document. So I think that would be great.
So I will give Adrian a copy of the PDF and he can post it as quickly as he can post it.
Thank you.
See you later today.
All right.
Any other questions? All right. Thank you, Ralph. Appreciate it.
Thank you.
All right. We have one more presentation and demo because this is an open hardware community. So we have to have something, you can see some hands-on demos, right? We've had presentations. Now let's actually see some real hardware. So without further ado, I'd like to turn it over to James and Tim. Well, they may not want you to put the finger in the hard drive itself, but yeah, we'll go. Did you want to start with the presentation first? And I think he's all set. No.
Well, I think we were talking about moving the monitor.
All right, give us just 2 minutes for logistics. For those on the phone, we actually have a setup in the back of the room.
For those of you on the phone, as well as those of you here, the Cloud Fast Fail spec is up in our contribution database. So if you guys need it, just go to the opencompute.org website, go under contributions, you'll see the contribution database, do a quick search on Cloud Fast Fail, or just fast fail, and the spec will show up. You can download it.
Thank you.
Yes.
When this is done,
You'll
when
contribute.
T10 approves it, I don't see any reason to contribute.
Oh, that's perfect. I love it. Does anybody want this?
James, do you want handheld or the other mic?
You want the clip on?
Do you want to make you? I'll make you the, yeah.
He's going to make you presenter. But
Okay.
you might want to put this on.
Okay, I should.
I made you the presenter. Do you want to just go plug in up front as well?
What?
You're presenter, but do you want to go plug in up front? My battery.
What?
My battery's gonna die, so it's dead.
Do I want it?
What's this?
This?
This.
No. Okay. I don't know what I'd do with it. Oh, okay. Where is that?
I got a box of Cat5 cables in the lab, just like this. All wrapped up.
Yeah, I think you tried that.
Well, you know, yeah. I still have Cat5 cables.
I thought I had.
Yes. Well, they're probably Cat5e. They probably are, yes, honestly. Who can keep up, you know? Some of them have been around for a while. They're probably real life Cat5. My first job, one of the first things I did was went down to Dallas. We bought a bunch of, back in the early 80s, we bought a bunch of computers and set up a Artisoft network with coax and splitters, and oh my gosh. It's terrible. Go ahead, Jane.
What? Where's my right?
Yeah, we see that screen. Only what's displayed up there.
You should see that screen.
That's exactly what we see on the web. You good to go?
Boy, a long way to get here, right? I'm James Borton from Seagate. This is Tim Walker.
Tim Walker.
Also from Seagate. I'm in the product line marketing group. I work with customers and working on long-term product strategies. And one of the things I've been focused on with some of my customers is the what we're calling the Mach2, which is our dual actuator product. And what we have here today is we have a demo in the back, which we'll show after the presentation, and some early performance results from some of our early engagements with our customers. And as the product is coming to market later, probably later this year. Yeah. I love this.
There. You just see the title slide? There we go.
All right.
Okay, the general issue of dual actuator has been discussed for probably a number of years. And the general issue is that as HDD capacities have been increasing, and with a single channel and an HDD, we're reaching an issue where, in some cases, with workloads represented by the blue line here, we're starting to get to a point where we may be crossing the line with against what we can deliver on an HDD given the capacity. As capacities increase, we're basically getting to a point where we cannot deliver the necessary throughput given the capacity of the device. And this gets us into the world of where we're going to need multi-actuator technology, more channels in this drive to increase the IOPS for our HDD. And this is the, basically the same graph from the more recent time frame. And we seem to be in a period now in this range of capacity that HDDs are needing those second actuator. Many customers have around the 8, 10, 12 IOPS per terabyte limits. And they're getting to the point where in some cases workloads are going to be causing them to have to short stroke the devices, basically rendering the capacity somewhat limited. So if you had a 14, 15, or 16 terabyte drive, but they can only support 5 or 6 IOPS per terabyte, they basically can't drive a capacity more than 8 or 10 terabytes, and they end up having to short stroke that device, which means they're either buying devices that they cannot drive the IOPS, or they're having to buy smaller devices, basically increasing the TCO of the HDD. And over, as capacities continue to increase, this problem becomes more and more significant. And that's why Seagate has gone into developing and manufacturing a dual actuator device. Question?
You have the same problem with Inspur. You have confidential.
Oh, I do?
So just for the record, this is not confidential, right?
No, it is not.
Okay.
It's the splitters seem to.
I know. It is confidential until you show it, and then allows me just to get the rate.
Right. We get these big, everybody's seen them, big PowerPoint templates from corporate that come down with.
I know.
But thank you for pointing that out. That this isn't confidential. When we post it up, all that stuff will be stripped out. Get it right this next time. Fundamentally, this the basic architecture of the dual actuator device is we basically have 2 channels and servos, a split actuator, and probably most of you have already seen the demo in the back. It's basically when it has 2 actuators, 2 sets of arms, 2 channels, transporting data up to through a common bus, SAS bus, and through a common cache. And that's basically, it's basically all it is. It's conceptually not that complicated. It takes a lot of engineering work. And there's a lot of
it's immensely complicated. Nobody but Seagate could have ever pulled it off. Okay.
A lot of concepts not very complicated, but there was a lot of considerations which probably Tim could talk to more about. Op vibe, attenuation between the actuators, read-write interference, things of that nature. It was a lot of work to get
to the point where we could deliver effectively up to double the IOPS on a device without too much interference, and basically the same footprint as standard HDD. You know, one thing that, and this is only a SAS-based device. It's got two LUNs. Thank you. It has two LUNs. There was a lot of discussion about this earlier, whether we could put this on SAS. SAS doesn't support multiple LUNs on a device. In that case, there was some ask, well, maybe we can do some sort of zone or device-based LBA management to split the LBAs on a device, and overall, that was viewed as you know, probably not an efficient way to go. This particular device will end up being basically plug and play. It's SAS, the same command sets. There's really no command set changes that need to be done, but at the same time, there's a lot of considerations which we're still working with the industry on, is LUN-based commands versus physical unit commands that you need to be aware of. For example, if you issue a stop unit on LUN 0 of a 2-LUN device, the device is very happy to spin down. And if you're in a VM environment, LUN 1, for example, it would just spin down, and that may or may not be the desired effect with in your data center. So we're looking at things like that. You know, there's a whole bunch of commands which are you know, things that need to be thought about: format units, spin up, spin down, sanitize, SCSI format, all these kinds of things which have different effects. For example, an extreme example, if you issued a sanitize to LUN 0, you can't ever undo that LUN 0 sanitize, which means LUN 0 will be basically inoperative until the whole drive ends up executing the sanitize. Because one way we've talked about doing this is possibly maybe deferring volume-specific commands down one LUN till we get the corresponding command in the other LUN. That's been one approach that's been considered. Or just deferring to the customers to let them manage the LUNs up in the stack so they don't do things that will affect the other LUN that they're not aware of. I mean, the performance goals, it's, you know, it's very simplistic. We're trying to you know, derive basically up to 2x on the sequential and also on the read IOs, random IOs and also sequential. And it's allowing us to, you know, leverage customer TCO areas which need high throughputs at low latencies at the highest capacity, which represent a lot of our hyperscale customers. And Tim, you might be able to talk to these graphs more effectively than I can.
I hate these graphs.
But those are the graphs we have. A man after my own heart.
These graphs are all over the building, I'm telling you. And so if you've been fortunate enough not to be too familiar with these graphs, what we've got is the result. It's a matrix that's been laid out here with transfer length and queue depth. And if you can read it, we got 4K, 32K, you know, 1 meg, 2 meg, 4 meg, with queue depth 1, 2, 4, 8, up to 64. And then so of course, for a 4K transfer, right, as soon as you start getting, since we're not afraid of queuing, and then this is why queuing is important for a hard drive. You can see it here, the difference of performance. If you allow the drive to sort internally, it can much more efficiently lay the data down. So you can see for every transfer link, as the queue depth goes up, transfer rate goes up. And then this is a discontinuity which has nothing to do with the data. It's just that we've gone out, now we've just indexed up to a new transfer link that we're going to go up, we're going to march up to the queue depth again.
And I mean, that's the mechanics of this graph. Without anything to compare it to, you know, it's just, this is what it is.
Yeah, it's showing, you know,
shows that
the two lines and the cumulative, you know, throughput.
Yes. Oh, yes. In that case, you're right. You can. In this case, what we're showing is each LUN individually. It's hard. I didn't even notice it. These are two lines on top of each other for LUN 0 and LUN 1, and then amazingly enough, when you add them together, you get this total that goes up to the top. So.
Yeah, and that's what the demo is going to show. Is we're able. It's a better comparison to a single actuator environment to a dual actuator environment, which is really what you want to see. Is we'll have that on the demo. You know, what is our throughput at a given latency target on a dual actuator Harrier versus a single actuator drive.
The important thing that this shows is that for this kind of architecture, I really didn't come here to sell you these drives. Is that even though the drive does have some shared, there is some shared resources. If you remember that block diagram, the cache is shared, and the interface is shared, and so we have some shared resources in the data path for a device like this. But under most workloads, the two units are independent. And we get, on a raw micro benchmark to the device, you really can get typically twice the IOPS or twice the throughput, twice the IOPS per terabyte, or twice the throughput, or you know, twice the megabytes per second per terabyte, which really isn't a number we talk about too much.
Strictly on the read.
Yeah.
There's a read advantage.
It's both. It works both ways.
These are the writes. These are random writes.
Yep.
Yeah, it works both ways.
And it works crossways. You can read on one and write on the other. The current state of the product is that we can seek on one actuator while we're writing and reading on the other. Which, I mean, and all kidding aside, that was you know, a lot of drive engineering. The great thing, what we think is good about the dual actuator approach to hard drives is allows our competitors to really apply what we really know how to do, which is servo, write, read, basic fundamentals of disk drives that we've been working on for decades, and this is a way we can scale it up. It scales up well. That's why we're proponents of it, and why we think it's important to the industry. It's deterministic. It scales linearly with however many actuators you feel like trying to cram into that space, and it, you know, very simple. In fact, I got this demo I want to show you just how simple it is to take advantage of this kind of approach to getting data on and off the disks. Mm-hmm. Yes, the drive behavior across. The question is does the behavior, is it consistent across the stroke? Yes, it's just as consistent. It's just as consistent as any hard drive is across the stroke. So you know, as you go into the ID, the transfer rates fall off, and if for random accesses where you have a lot of head movement, you have the same impacts on any individual actuator, depending on how you manage. Me conceptually, the work I do, I work for Seagate Research in the systems. In my mind, these things are a drive that you have, you know, that it's got these two parallel paths, and it's up to us to divvy the work, to divide the workload up, just like anytime you have two resources, to divide the workload up to where, you know, one is not saturated, and you can, and what am I trying to say? You know, divide the workload up so that you can get
keep both actuators busy all the time.
This assumes that the host system, which controls what workload each one, is balanced.
It has to, because we do not. We're single port SAS with 2 LUNs, and they are independent. Again, there are some shared resources, but they're managed independently. So like you saw, the cache is common between the 2 channels, but we track, whose is whose. We don't, if you send data down to LUN 0, in the LBA spaces on these LUNs, both start at 0, and so if you send data down to LUN 0, it doesn't end up on LUN 1, and you can't pull it out of LUN 1 either. They truly are independent. That is because that is the most foolproof way, we think, for people who use them to be able to take advantage. We talked about, like James said, we talked about, should the drive divvy this stuff up? Should the drive stripe it? Or whatever. But what the conclusion we came to is we thought we could come up with some good schemes to divide the workload up between the actuators. So we knew whatever scheme we came up with it would only suit, the scheme I came up with today just suits my view of data center workloads today, right? It doesn't really suit everybody else's workload. So our work with our key lead customers was they say they can handle it. And in fact, they would prefer that they handle it instead of us handling it.
The best way for them to control latency is for them to have all the knobs.
Right. No. So,
repeat it.
Yeah, so the question is, what's the impact on reliability? Now, and you're not the first person to ask that. So the drive has a higher component count. So anybody, your reliability engineers would, if you increase component count, you decrease reliability. But that's really a small factor in driving the reliability. There is no, in other words, we maintain the same level of tolerance, on the things that affect hard drive reliability, or the main things that affect it are the HDI, the head disk interface. This is the same. That hasn't changed. Because if you look at the demo unit back there, the physical unit, all we did was just take the actuator, which is about this tall, with all you said, and just saw it in half, and put an extra set of bearings in the middle, and actuate them independently. And so everything that goes into hard drive reliability that surrounds the VCM, the actuator and the heads, we carried that over. That's why I say that this kind of approach is good for hard drive manufacturers, because it takes what we've already mastered and applies it a little bit differently.
So, there are trade-offs. So you have more components, so the cost of components is higher for the product, right? So,
right. It's not free.
If this had no downsides, all drives would be like this, right?
That's right.
So can you comment on that, on the trade-offs that were made this is a performance play, and there were some trade-offs that were made.
The trade-offs that we've made are all in cost, really, because since with 2 actuators, you have two voice coils, you have a more complex magnet assembly, you have a more complex process to assemble it. So those in the factory, so those are all impacts. We have to add more electronics, because now you have 2 channels, 2 read-write channels. You have 2 servo controllers. So we have more, we have more MIPS requirements in the SoC. Power can go up. And really, if you're going to apply a workload, so if you apply the same workload to it, to a single spindle drive, and you manage your workload carefully, well, obviously you could just feed all the workload to one LUN, and then you'd be analogous to a single actuator drive. But if you're going to drive both actuators and drive the crap out of them and get your IOPS that you need, so yes, power's going to go up.
Actually, the device power will go up, like you say, but the IOPS per watt
went down. Yes, went down. Yeah. Yes. And that is something we're looking to be able to show more clearly, is IOPS per watt.
The there a difference with the sequential? Is there the metrics change a little bit from a sequential write, read? Okay, you're getting there. Thank you.
Well, yeah, it's sequential reads, sequential writes. You know, I don't know if you want to talk to the sequential reads or writes more.
Really, it's essentially sequentials can be trickier because of the architecture with the shared cache. Because especially sequential and queued. But I mean, John, I think we're just currently the way it looks, it's double. You know, there's no inherent impact on the way the drive behaves for sequential workloads.
So it's similar to the prior performance.
It's weird. You know, our disk rates are current with our current products, and track pitch is current with current products. So our sequential throughput per channel is state of the art with our nearline drives, and so you get double.
Yeah, but you made a good point about cost. I mean, obviously, is dual actuator drive, you're adding cost into it. Goes into cost per IOP. However, it has other positive effects on TCO because you can drive more IOPS per given capacity and given footprint, and more IOPS per watt. So the cost per raw terabyte is higher as far as the actual storage cost, but the overall cost per terabyte, if you look at the overall infrastructure, changes based upon what throughput you have. If you have the throughput to drive 20 terabyte drives, there's a big savings in power and floor space on a TCO model. I mean, there's obviously it changes the equations because dollars per terabyte is going up, but the floor space cost may be going down, and dollars per watt power is going down, et cetera.
I mean, if your workload requires, on the average of 10 IOPS per terabyte, then, and currently a spindle is good for 70, 80 IOPS. One actuator is good for 70 or 80 short tranche length IOPS. Then once you get up above 8 or 10 terabyte drive capacity, you're done. You're done. You're stuck. If your workload really requires that, you can't put your hard drive. You can't push your hard drive capacity up anymore. And so you get a 16 terabyte drive coming out here later on this year. You only use 10 terabytes of it. And so your options is to pay a little bit more. I'm an engineer. I don't really know anything about how much things cost. But you can pay a little bit more and get an extra actuator and keep one drive, or you're gonna have to buy 2 10s. And so that's what our customers came to us with. That's the issue they came to us with.
Or short stroke. I mean, some customers are short stroke.
You can buy the 16 and short stroke it down to 10.
Well, you can add more caching.
You buy flash.
More flash, yeah.
So is the difference between LUN 0 and LUN 1 sequential rate in lower block count that inherent to having a multi-actuator, or is it just the nature of
I don't know of anything that is inherent to the multi-actuator. Yes, or even that could even be just that drive.
If there's something that does, it might be. If there's something that's causing that, it might be somehow related to a shared queue. The
shared queue is tricky.
Yeah.
Because shared command queue and shared cache.
Shared queuing and caching. There's been a lot of firmware tuning, to try to squeeze down these differences, because you can Pardon me?
The command queue, a modern SAS controller, the command queue is all on hardware, and it's just currently just one. Yes. Obviously, we know what run is. Yeah. Yes. Mm-hmm.
I think this is impressive and congratulations because this is very nice. I got a couple questions because of you increase the electronics and parts inside the drive, and any concern on the thermal behavior. That number one, and also on this plot you can see some of the red and the green not in sync. Do you know why?
I don't know why the red and green are not in sync on this chart. Anybody know why? I don't know why. I'll take that as an action. On thermals, I mean, we do have higher heat. We do have higher power dissipation. We kind of talked about that, but we have plenty of thermal capability, the thermal transfer coefficient on these things to move the heat from the voice coil out to the case is extremely low, and so we don't really. That's not an issue. Plus, for years, hard drives have monitored their VCM temperatures internally to make sure that we don't smoke them, because and so what I'm trying to say is we do generate more heat. The heat is easy to get out of the enclosure, and in the case where a drive does not have adequate cooling, like it's sitting out on a bench or something, everybody's drive monitors their temperature and backs off to keep from hurting themselves. So really, I think we're okay. I think we're covered. No, for example, our thermal limits of operation. No, it's the same. The shock and vibe is the same. Thermal's the same. Power, the voltage. I mean, it really is. Like you set it in there, and that's what I'm going to show you. If you for an architecture like this, you can put it in there and very easily take advantage of it. Which is the beauty of the SAS. I never thought I'd say this. I'm the NVMe guy, but the beauty of the SAS flexibility is that you can put this in and get it to run.
How long do you think two actuators will last?
Not taking that one. Depends on the price of flash. The flash, the cheaper flash gets, the harder this, I mean, honestly, an approach like this puts rotating, allows rotating storage to be viable, to support a wider range of customer workloads. And so, it helps our customers buy cheap hard drives, not cheap, but inexpensive. Thank you. Yeah, it's compared to flash. Yeah, these aren't cheap, but compared to flash, they're much cheaper. They're cost effective. Thank you. Cost effective storage, and it's important to keeping. Our customers want to buy cost effective storage, and we're doing our best. So they need 4, we'll give them 4.
So I understand what the two actuators and random sequences or read and write, you gain a lot more flexibility with the actuators. But I'm at a loss because if you have the same number of heads, ladders inside the system, why your sequential would double?
Because since there's 2 channels.
Okay. The limitation's not it's in the channel. Duplicating the channel.
Right. Correct.
You have typically get used to
the 2 active
data.
Yeah.
But in sense, because you still have the same number of heads, that if you're doing a full sequential write and read, I would expect it to be very similar in a number.
We write a track. It still takes the same amount of time to write a track, but we can write 2 tracks simultaneously. If the drive can, if the host sends the data down to the 2 LUNs. If you do, if the host is going to do a pack write and he starts with LUN 0 and starts with LBA 0, LUN 0, works his all the way up to the top of that, and then goes to LUN 1 and works his way all the way through that, yes, it takes the same amount of time. But if the host just starts both LUNs and just then you're done in half the time. Because these drives, the interface speed, these are 12 gig SAS, as everybody is. So interface speed is not an issue. Yes. So, yes. So these things are not, you can't, with an architecture like this, you cannot just like drop it into your system and double the performance. But I will show you how easy it is to do that. Yeah.
I mean, a host sees these as two drives. Yeah. And I mean, that's been some of the discussion with some of the customers is what level of awareness do they need to have? And maybe none, but however, like some of the SAS commands we were talking about, if you're doing power management on, you have to be a little bit careful. You have to be a little bit more careful there.
We're gonna set this half.
Yeah.
Power.
And put this half to sleep.
Half of each drive. We're gonna save half the power, right?
Right. That'll get fixed. I'm confident. And then.
That's high level awareness. That's easy stuff.
Yes.
The granularity, of course, that we do.
Mm-hmm.
Any other questions that we can just jump into the?
Let me put this thing. Let me show you what we got.
Well, I'm setting up the demo. I want to do a real quick tie together the last three presentations. So this, as well as the fast fail, they may seem a little bit different, but they're actually solving very similar challenges for us. When we look at hyperscale or distributed workloads, and you have read constraints, let's say your read tolerance is 30 milliseconds. So on a single actuator, you're going to get some depth in your queue. Maybe that's 3 or 4. But when you go to multi-actuator, now you can have 2 queues the same to get deterministic latency. That brings your average latency down. Then when you look at the fast fail, that's more not for average latency, but your tail latency. So those IOs that sit out there at hundreds of milliseconds or seconds, the goal is that, we can do that differently. We'll send that to another drive, another spindle, another machine. So if you combine the two things, you cut off a lot more of your tail, send that to another aspect of a distributed system, and then things like multi-actuator allow us to then bring a step function down of how many IOs that we can actually get out of a specific capacity. I think that's what you're going to see in the demo, is that if you have that latency target, again, on reads, caching sounds great on paper. It works for a little bit, but in a really wide data set, you're going to find out that read caches end up being a little less helpful than you might expect. Write caches, you can hide it. We talked about that earlier in the day. You can hide that from the user, but read cache really doesn't hide very much, depending on your workload. Again, there may be workloads that a small read cache will help you with.
How's it looking, Tim?
Can you give me a? I'm requesting a.
There you go.
Okay, am I the
presenter now?
Okay.
Oh. Hold on, let me grab the laptop.
Is my microphone not working?
Yeah, I'll get you. I need to.
Can you hear me?
Hold on,
What? Oh, you know how all this stuff works.
This won't take very long.
Tim, you're all set. Just let me plug this into the room.
Oh, okay. This is a real simple system. It's just got a Windows Server 2016 running on it. And what I did was I put one of these drives in. There we go. Whoops. Okay. And you may not be familiar with this. Depends on how much Windows Server you work on. But this is a storage pool, which is what I did was I set up all I did was set up a storage pool. It's like 6 clicks. This Harrier pool up here, and this is what the storage pool consists of. It consists of the 2 LUNs on a single Harrier. So once you do that, then 4 clicks later, you have the virtual disk set up, and then 4 clicks after that, this is now drive E. Okay, so that's what it takes. That's how much work it is to take a drive with this kind of architecture. and get it integrated into your system to be able to take advantage of it. So now it's set up for a stripe. So it's just set for a basic stripe. There's no redundancy or anything. And so and it's storage spaces. I don't even know how. I didn't do anything to the stripe size. I didn't do anything. It's all default. And which is the way I think you might use it if you got one of these to look at. And so yeah, it's a RAID 1, striped RAID 1, RAID 0. Sorry, it's not mirrored. I got my RAID mixed up. And then so what this is this is running. It's been running this afternoon. This is like a little block diagram of what our system looks like. I have 2 Harriers really, 2 of these dual actuator drives. One of them is set up the way I said. The 2 LUNs go into a virtual disk up to the application. The other one is, in comparison, just one of the LUNs into a virtual disk up to the application. I did 1 LUN into a virtual disk. You normally wouldn't do that, but because I wanted the I/O paths to be as common as possible, down through the storage spaces, so that any overhead added by the system would be consistent across the 2. And then what these charts show, the top chart shows our average read latency. We're doing random 32K random reads over the whole disk. The test runs for 7 seconds using disk speed, which is the Microsoft micro benchmark tool. And then disk speed spits out the performance parameters, and we collect them and display them. The blue line on the top shows the dual actuator virtual disk performance, the queue depth, IOPS, the average latency in milliseconds, and the throughput in megabytes per second. The gold bar is the single actuator, same workload. They run simultaneously. And again, it's queue depth, the IOPS, average latency, and throughput. And then what we were asked to provide today was, because you guys are driven by latency. So what we do is we set a target average latency of 30 milliseconds. And then the tool adjusts the queue depth to keep the throughput, to keep the average latency at about 30 milliseconds. Down here is your latency distribution. I have a license for this, really. I put the system together and didn't put my key on it, trust me. So this is your latency, your cumulative latency distribution chart by 9s. So here's your 2 9s, 3 9s, 4 9s, 5 9s cumulative latency distribution. So what this is showing right now is that it's only a 7-second test, so we're not getting 9 9s worth of data out of this. But the tool is reporting it, and really the way to interpret that is that 100% of the commands are within this latency window. So what you can see is the single spin on this workload, and with this test time, this is kind of noisy. And so sometimes the single spindle drive has a better latency distribution. Sometimes use the single actuator drive is better. Sometimes the single actuator is. Right now, this one's showing that the one target one is slightly faster. You can see the 3 9s is about 140 milliseconds. Up and now, in this case, it's about 155 3 9s for the dual and up almost 200 for the single. Really, but this does show, the intent of this is to show you guys that, to show you the data. That for a target latency, in this case of 30 milliseconds, and this has nothing to do with the fact that it's a dual actuator drive. We could have done the same thing, just take 2 drives and send them up in storage space, so you get the same results. And that's exactly what I want to show you. It behaves like 2 drives. And so all your strategies for latency and redundancy management, although these don't think these two LUNs, there is no redundancy gained by putting the data on these two LUNs. All the failure modes on these things, 99% of them are common to both of them. But the strategy that we use to handle, to control workload to hard drives to reach our performance goals is they don't change with this kind of approach. You just do it the same way. So we combined the two halves of this drive into one striped drive, and we get the appropriate performance. So in our case, maintaining the same average latency and oftentimes comparable tails, but we probably shouldn't pay too much attention to that with these parameters. Our queue depth is we can maintain a higher queue depth, 5 or 6 versus 3. Our IOPS are almost double, and our throughput is, almost double. It's not all the way double, and but for a system level load like this, where we are feeding this into the top of the stack. Well, we're not using the file system; it's not all the way to the top of the stack. But we're going into the virtual disk. Then I'm not too upset about not getting exactly double. So this is all it takes to take this kind of architecture and see an immediate and worthwhile improvement in performance for just slight additional cost. That's really all I have. Sure. We have a demo drive back here that's not a real drive.
Yeah, I think everyone wants to go back and look. The screen
do you want to
setup's over in the back corner.
Yeah, there's the one here running.
All right, if some people go back in the back and take a look at that. If not, thank you all for coming. We really appreciate this. Obviously, it's only the second face-to-face. These will evolve over time. But I'm hopeful that some of these conversations and presentations will start to spark things that you want to bring to either the community, kick off work streams, whatever that might be. So please reach out, get involved. Glad to see you all here in person. Thank you.